So he's even when he was alive. And of course the accelerators giving both stable and unstable beams, which are required for pursuit of nuclear physics, momentum and isospin. These are all some of the recurring themes of any current day nuclear physics research. Talking of high energy nuclear physics, of course we all know the familiar phase diagram of water, ice and vapor, steam, and we have decision making points, ice to water, water to steam, and this is what similar thing we can also extend to study of the nuclear matter. Here also we can plot it in terms of the chemical potential and temperature. So the normal nucleus is sitting here. So when you subject it to heat, then we have to have a liquid to gas phase transition. And similarly, when you go to higher temperature and higher density, we also look for another phase transition. Now it is a phase transition of nucleons, and that is protons and neutrons becoming quarks and gluons. This is the other transition. The critical points are here, and beyond this, the phase transition becomes second order phase transition. But it is of interest to see this kind of phase changes, as we know in the normal water, ice and vapor. So this is the triple critical point, the point where with a small change in temperature or pressure, it can go to different phases. And similarly, we have this critical point where it becomes a smooth transition, which is the second order phase transition. So similar things are being invoked even in the case of nuclear matter. And we have done a lot of work at CERN looking for these phase transitions. And it has been now established that the hadrons, the nucleons and neutrons and protons, indeed go through this phase transition to quarks and gluons and to quark degrees of nuclei. As you know that proton and neutrons do not have heavy quarks, so if you use a heavy quark particle as a probe and then make them enter the nucleon, then it is possible to see the distribution of quark degrees of freedom. The chiral symmetry breaking and mass of particles is again an important area. Hadron structure, medium modification, hypernuclei, glue balls. Of course, Professor Radhe Shyam is here. I'm sure he will talk about many of this hadron physics later. But again, why it is interesting, because we want to have many things happening in nuclear physics and connected to other disciplines of physics. For instance, as I told you, some of the nuclear physics findings have a bearing on astrophysics, also bearing on particle physics. And here I give you some more examples which I have taken from literature. One of the things which was found, instead of the non-interacting QGP gas, what was found experimentally was strongly interacting, almost like an ideal fluid with almost zero viscosity. And this is something which was not expected from theory to start with. So this is what we have seen. We did see QGP, but not the way we predicted. Now shear viscosity divided by entropy is roughly equal to 1 by 4 pi. This is what has been found. And of course, background is a serious problem. So underground lab is the solution. Of course, Gran Sasso, they already have the Luna facility. And what is happening currently, it is believed the salt mines are better because they will be free from uranium and thorium gamma background. So people are looking into some of these favorable sites. And million volt accelerator instead of kilovolt accelerator are being installed underground. Luna, the Diana, there may be many others. So important cross sections which have been mentioned. Of course, they have been measured earlier, but they still remain to be measured. And the challenge is to measure at very low energy, close to the gamma peak. So carbon-carbon, carbon alpha ion, neon alpha ion. Of course, these are the neutron-producing stellar reactions which later are useful for building up of elements beyond iron. So if you don't know this source or the intensity of production, you cannot make proper prediction of the heavier element formation. So they are very important to measure with good precision. And there are also cross sections. Of course, one can have a large number of the list of cross sections which require better precision and of course with better reliability, so that about the mass, size, radius, moments, and the same thing should be repeated when we have few thousands of nuclei now. What combination of neutron and proton can form a bound nucleus? What are the limits of stability as a function of mass number, proton number, and neutron number? Liquid drop was a single shell model. Of course, this is a recurring theme all the time in nuclear physics. Of course, better models have come. New decay modes, 2 proton decay, 2 neutron decay, n equal to z nuclei. Again, we started nuclear physics with n equal to z nuclei and understanding them, mirror nuclei. Many things we learned about nuclear force and things like that through mirror nuclei studies. And a similar thing is supposed to be done with heavier mass numbers. This is all feasible because of the availability of radioactive ion beams now. List, of course, neutron-rich nuclei, unusual structures. Let me highlight on this. Enhanced quadrupole collectivity for this nucleus. See, many of the things were not predicted by any theory. They have been seen first time in the experiment, and some, of course, have been predicted and confirmed. Mass formula and add important terms based on some physics considerations and some of the models which are in use. The RMS deviation has been found to be almost 600 keV or so. So our empirical prescription based on sound physics seems to be doing a reasonably good job of almost all the nuclei we have seen in experiments. This is just to say this is a neutron, a number of protons and number of neutrons, and what we started is only these 300 nuclei along the line of stability, and we have a whole world to explore. This is what I meant by you can be a few thousand nuclei which all have not been seen. We can go this way to super heavy mass, the proton drip line where the proton binding energy becomes zero, and this is the neutron drip line where the neutron comes out like alpha decay. So the lot of scope and lot of work still remains to be done. And also told you because of astrophysics connection, the nucleosynthesis, so all these cross sections and nuclei are of interest. I've just given a table here starting from n equal to 4, helium-6 and helium-8 have been in strong focus. A lot of papers have been published using these helium-6 and helium-8 beams, and you can see that helium-6 lives for only 800 milliseconds, 8 lives for 120 milliseconds, and you can see the separation energy, neutron separation energy, 2 neutron separation energy is even smaller than removing 1 neutron. Similarly here, this is also smaller than 1. These are all various things, lithium isotopes, beryllium isotopes, and you can see boron 8, I'm just repeating that, oxygen 24, nitrogen 23, and carbon 22. All of them have 16. And this takes care of the proton distribution, and this gives a measure how far outside the proton distribution the neutrons are spread. And you can see that in lithium-11, one of the very popular candidates, halonuclei, which has been thoroughly studied, the neutron distribution spreads far away from the proton distribution. This is what we call the halonuclei. The neutron distribution radius is almost 3.4, whereas the proton radius is only 2.4. And there are other examples here. Gives you an idea how big, even though it is lithium-11, its size is as big as lead-208, which is of course a compact body. Again, you see this carbon-22 is also a halonucleus. Matter radius is 5.4. Just neighboring mass number 24 and 23, their matter radius is only this much. So you can see a dramatic change just changing by 1 neutron or 1 proton. So this is what we call the breakdown of R equal to R naught a power 1/3 rule. If it is, this rule is valid, then this should have been similar to this. So if the above scaling is true, then 22 carbon should have been having a radius of only this much, whereas it is this. So it is as good as large as 90 zirconium. Similarly, 11 lithium, as I told you, the central portion is as good as calcium. And there are some structural changes which have been seen. The radius plotted here on the y-axis against mass number for magnesium isotopes. And you can see with increasing neutron number, the size becomes smaller, and then it changes and then goes up again. So this is what is called the inversion, where again there is a kind of change in the size from decreasing to increasing. And then we ask our question, these are all famous magic numbers, 2, 8, 20, 28, 50, 82, 126. We want to know, even when the neutron number and proton numbers are changed drastically from stable nuclei, whether this magicity is preserved. It so happens that something is happening around 126, similarly something is happening around 82, and similar things are noticed at 50. So that means, even though the neutron number and proton number, because we are talking about different nuclei, that means the proton numbers are different, and neutron number is changing, and you see that the magicity is well preserved. Of course, this was not known to us before we did these experiments or measurements. Nuclear structure. Again, the separation energy, which is one of the important measurements. And you can see here cadmium, helium, tin, antimony, tellurium, and barium. And usually the shell thing is there is a gap which is noticed, and this gap seems to be again preserved. Of course, there is a small reduction, but otherwise there is a gap between N84 and N82. Because N82 is a magic number, and this seems to be preserved. This is another interesting which has been noticed. Again, what is plotted is size as a function of neutron number for different nuclei, starting from molybdenum to krypton. And what I want you to notice in this part, the size seems to be monotonically increasing. And when you come to niobium, there is a kink noticed. And this kink apparently disappears by the time you come to krypton. So it was not there in molybdenum, it was not there in krypton, but in between this kink is noticed. So this, the theoreticians have explained as nuclear quantum phase transition of something to do with nuclear shape. NP changed their orbit occupation in this nucleus. It's come in the last 2 years or so. This is something very interesting. All these experiments are possible because we have now radioactive ion beams. This is another very interesting thing again for structure. You know, this what I have given here is the excitation energy of the first excited state in all these thin isotopes, 98 to 137, where experimental measurements are available, and their half-lives. Of course, as you can see, these are the stable isotopes of tin, and these are all unstable, but their properties have been measured. Very interestingly, when you go to this 132 tin, where it is, of course, it is a doubly closed shell nucleus, so you can see that excited state is 4.04. As soon as you come out of that magicity, you find all these excited states are nearly the same. This again, of course, explanations are available, but this is something very interesting. What is plotted here, this is a tin isotopes. I've just shown the first excited state, and you can see some kind of constancy. If you leave out that real magic number nucleus, rest of the nucleus, even though neutron number is changing, the first excited state, energy is not changing. And similar thing is happening in cadmium, and similar thing is happening in tellurium, which are very close to tin on either side. One is 2 protons less, and the other one 2 protons above. Actually, I did this compilation, I didn't know, but this could not be continued beyond this. I found plus or minus 2 protons, a similar behavior is observed, whatever was reported for tin. I'm sorry about the poor quality, I took it from a paper. I think again this is to highlight the importance of not only two nucleon interaction, but also multinucleon interaction. And this even for light nucleus like boron 10, 11 carbon isotopes, the level diagram can be better understood or explained if you invoke the 3 nucleon force as well. This is also another important thing, the mirror nuclei concept. 54 iron and 54 nickel. 54 nickel has got 28 protons and 26 neutrons, and this one has got, so these are mirror nuclei. And you can see here the excited states. See these higher excited states, these energies are higher than this. 2,6 and 2,5, 3,0, 2,9, 3,7, 3,4. Whereas the first excited state, this energy is lower than this. So if you plot this as a function of the spin, you can see a dip and again all going up. This is what they call it J equal to 2 anomaly. And of course it has been understood. I just wanted to say that these are all simple things. Even there are some new things happening. It is just basically a Coulomb difference, Coulomb energy difference. And there also this spin factor is very important. And so this is a reversal of the trend. It should have been all the time going up, but it has come down and then again gone up. This is again the role of neutron-proton pairing and shape influence on nuclear structure. Again, there are a number of things given. In some case, the energy difference doesn't change with J. In some cases, it decreases. In some cases, it increases. So I just to say that again, there are interesting things happening in nuclear structure. Nuclear reaction, of course, I'm not giving any figures. A lot of work is being done also in the country using our cyclotrons and pelotrons. Again, the themes are deep subbarrier energies, weakly bound projectiles, and then nuclear fission is one of the themes where a lot of people are working in the country. Jain dipole resonance, IMF, ICF, dipole polarizability, level density, shell structure, alpha protection, coupled channels and dynamic calculations. Both stable ion beams and radioactive ion beams have been employed. Super heavy element research. You all know that 114 has been named as flerobium, 116 has been named as livermorium, and 118 evidence is there. Right now 117 also some evidence has been reported, and currently experimental work is going on for 119 and 120. So you can see the periodic table is really moving ahead. Of course, most of the work is done at either GSI or Dubna, and of course Japan also has come in the, and little bit of work is still continuing to be done at Lawrence Berkeley Lab. So this is just to say that again the role of shell closure in a pure liquid drop picture, that is what gave rise to this possibility of finding these super heavy nuclei, and experimentally it is very reassuring that things are happening the way it was predicted, and we may reach charge number 120 or beyond in the next few years. Again, that will be a success for the theory over the experimental finding. This is just to say the kind of projectiles and targets which have been used, starting from 107, and originally they were using closed shell targets with this kind of projectiles. It's the cold fusion route, the hot fusion route. Again, there may be many more examples. Professor Gupta is here. He has been working in this field for many years. The various combinations of projectile targets which will be favorable for observation of super heavy elements. Of course, there have been predictions that chromium and other isotopes also should be tried. There are certain things advantageous, certain things not advantageous. So hope of finding super heavy looks very bright. These are some of the, this is in progress at GSI. So 120, 119, that is where of course these are all very painstaking experiments where only 2-3 atoms are produced, and you have to run this experiment for several months before you can really say that such a thing has happened. So to summarize, I have just given you some overview of expanding nuclear landscape, evolution and excitement, significant achievements in all aspects, upcoming facilities. Of course, as you all know, we want to go to higher and higher energies and also higher and higher intensities. The FAIR facility which is coming up is supposed to be the intensity frontier. Both stable and ion beams and radioactive ion beams are used for this kind of investigations. Nuclear physics continues to be interesting and challenging. I have tried to give you several examples. Many things have happened which were not predicted. Significant progress towards understanding in terms of fundamental constants. Finally, that is our aim. So I thank you for your attention.
From Punjab University, Chandigarh. And he retired. From there, he retired as a professor in 2000. He continues to be as active even after 12 years of his formal retirement. Informally, he has never retired. Dr. Gupta is a theoretical nuclear physicist in 1971 and PhD in 1977 from Banaras Hindu University. He has been employed at the Saha Institute of Nuclear Physics, Kolkata, where he has been a senior professor since 2004 and nuclear physics many times. Professor Jain has made significant contributions to various areas of theoretical nuclear physics. To name a few, effective Lagrangian approach to meson production in nucleon-nucleon collisions, coupled channels K-matrix approach to meson photoproduction, analysis of baryonic resonances from cross-sections and polarization of observables, production of hypernuclei with hadronic and electromagnetic probes.
Side love.